So to put things into perspective, let's look at the force acting on a typical cell phone due to gravity. Now, just as we saw before, the force acting on an object is equal to its mass times the acceleration it experiences. And so, an average cell phone weighs about 150 grams, which is equal to 0.15 kilograms. And multiply that by acceleration due to gravity, which is 9.8 meters per second squared. That gives us a force of 1.47 kilogram meters per second squared, or 1.47 newtons. That means that when you're holding a cell phone up against gravity, when you're fighting gravity, just keep it in place, you are putting a force on that cell phone of 1.47, or about 1.5 newtons, which really is not very much. A newton is really not very much force. The last of Newton's laws of motion is Newton's third law, which says that for every action there's an equal and opposite reaction. That means that every time two objects interact, there's a pair of forces acting on the two objects. Now, the size of the force on the first object is equal to the size of the force on the second object. And the direction of the force on the first object is opposite to the direction of the force on the second object. These forces always come in pairs. They're equal in magnitude and opposite in direction, action-reaction force pairs. Let's think about a boat moving through water. The boat uses a propeller. The propeller pushes water backwards. So the boat pushes the water backwards. Now, that's fine, but that doesn't move the boat forward. What actually does move the boat forward is the fact that when you push the water backwards via the propeller, the water pushes back on the propeller forward. And so the boat pushes on the water backward, the water pushes back on the boat, pushing it forward and making it go. Now, you might think, if these are opposite in direction but equal in magnitude, why don't they just cancel out? The answer is that one force is acting on the water and the other force is acting on the boat. If both forces were acting on the boat, for instance, then they would cancel out. If you had a force acting this way on the boat and another force acting this way on the boat, those two forces would cancel out. The boat wouldn't go anywhere. In this action-reaction force pair, one force acts on the water, the other one acts on the boat. And again, in this situation, the size of the force on the water equals the size of the force on the boat. It's their directions that are opposite. And so to summarize, Newton's first law says that objects maintain their state of motion unless acted upon by an unbalanced force. It's that unbalanced that matters there. There are always forces acting on whatever object due to gravity, the normal force that supports an object when it sits on a horizontal surface, for instance. Friction is acting. It's the unbalanced force, it's the net force that's responsible for an object's change in state of motion. Newton's second law says that force equals mass times acceleration. You can also rearrange that to say that acceleration equals force divided by mass, or if you know the force acting on an object and how fast it's accelerating, you can also figure out its mass. Mass equals force divided by acceleration. Newton's third law says that for every action there's an equal and opposite reaction. And so let's look at a couple of forces that are important, and let's also do a couple examples. So let's look at the normal force. Whenever an object is sitting on a horizontal surface and not accelerating through the surface, now, if you think about it, there's going to be, let's draw a free body diagram about it, there's going to be always for an object sitting on a surface, there's always going to be a force due to gravity pulling down on it. Now, because this is not accelerating through the surface, because it's not accelerating, this can't be the only force. Why? Because if it were, then this would also be the net force, and that would cause an acceleration. And so, there must also be a force acting upward to balance that gravitational force, and this force, this balancing force, is called the normal, given the symbol Fn, F sub n. So the normal force acts perpendicular to the surface and opposite to any forces that push or pull the object into the surface. So let's calculate a couple of normals. One for a 100 kilogram body acting on flat ground, and second for a 100 kilogram body sitting on a 20-degree ramp. So first, for an object sitting on flat ground, here's the object, again with force of gravity, force, the normal force. Now, because there's no acceleration for this object in the vertical, the up or down, we can say that F net equals 0. The net force acting on the object in the vertical is 0, which means that the net force is just the sum of the forces in one direction, that Fn plus Fg, those are the two forces, and the sum of the forces equals F net. The sum of the forces acting in the y direction equals 0. Now, rearranging this, F net equals the negative of Fg. I just moved this guy over across the equal sign, and because it crossed the equal sign, it became negative. So Fn equals the negative of Fg. In this case, the negative just means that Fn and Fg are in opposite directions. When you're talking about vectors, the negative only refers to direction. It's not a negative force, it's not imploding or anything. It's just that Fn, the normal force, is opposite in direction to the gravitational force. However, they are equal in magnitude. So, if we figure out Fg, Fn will be equal to that in magnitude, opposite in direction. We can see that they're opposite in direction over here. Now, Fg, the force due to gravity is always equal to the object's mass times its acceleration due to gravity. That's sometimes written as A sub g. It's sometimes written as mg. This g is acceleration due to gravity and is equal to 9.8 meters per second squared. And so, for this 100 kilogram object, we have the force of gravity equaling mass of 100 kilograms times acceleration due to gravity, 9.8 meters per second squared. Doing that math, we get 980 kilogram meters per second squared, which is equal to 980 newtons. It's useful to remember that a kilogram meter per second squared is equal to a newton, because say we're doing this backwards and we wanted to find the acceleration, we'd take gravity, the force of gravity, force due to gravity, divided by mass. Now, if we just kept the force of gravity in newtons, we wouldn't cancel, our units wouldn't cancel nicely. If we convert newtons first in that calculation to kilogram meters per second squared, then kilograms cancel, and we can see that gravity takes units of meters per second squared, which is correct. This is useful because when you're doing these calculations, if your answer doesn't end up in units that match with the quantity, if your acceleration, for instance, if you found an acceleration with units of kilograms per second squared, you know that there's something wrong, because accelerations don't come in kilograms per second squared, they come in meters per second squared. In question B, we're asked to find the normal force that, again, is the perpendicular force coming from the surface which supports an object on a 20-degree ramp. Now, this ramp may not be degrees to scale, but let's say that it is 20 degrees. Let's draw the object on our ramp, and let's draw the force due to gravity being down. This is the same 100 kilogram object, so the force due to gravity on this object is 980 newtons. Now, the normal force will be acting perpendicular to the surface that the object sits on. So in a situation on a ramp, which you will see a lot this semester, we're going to break these. We're going to get out of the x and y axes, and we're going to use a sort of twisted axis, or turned axis. We'll call this direction the y prime direction, and this direction the x prime direction. And so, in the x prime direction, we've got some component of gravity. We'll call it FG y prime. There'll be some FG x prime here, the x prime component of gravity. FG y prime opposing Fn. Now these two are going to be the only forces acting in the y prime direction. And so just as before, because they're the only forces acting, and because this object is not accelerating off the ramp, it's not accelerating through the ramp, in fact it's not accelerating at all, because in this direction there's no acceleration, the net force must be 0. So in the y prime direction, F net equals 0, which means that Fn plus Fgy prime equals 0, because the net force is just the sum of the forces acting in one direction, which means that Fn equals negative Fgy prime. Good. So we know that the normal force is equal to this y prime component of the gravitational force. So if we calculate this, if we find the magnitude of Fgy prime, then Fn will have the same magnitude. How do we do that? Well, let's look at this triangle here. let's look at this triangle right here. Now, this is 20. This angle over here is formed between the horizontal and this force due to gravity, which is by definition vertical, which means that this is a 90-degree angle, which means that this right here is a 70-degree angle. If you look over here at these two angles, because they're opposite sides of two intersecting lines, this angle is also 70 degrees. And if you look at this angle here, this is y prime, which we set up as perpendicular to the ramp. So that's a right angle, which means that this angle right here, 70, 90, this must be 20 degrees. Now, in this gravity triangle, we have FG, we have FG y prime, we have FG x prime. And this being 20 degrees, FGY prime is adjacent to the 20-degree angle, and FG is the hypotenuse in this triangle. So, given that this is the adjacent angle, let's take a look at what the cos of 20 equals. Cos 20 degrees equals adjacent over hypotenuse. That's simple trig. Cos 20 equals adjacent over hypotenuse. In this case, the adjacent side is synonymous with FGY prime, and the hypotenuse synonymous with FG. So if we want to know what FG is, we can solve for that. Sorry, if we want to know what FGY is, we can solve for that. FGY, then, rearranging this equation, is equal to FG cos 20 degrees. Remembering that FG is equal to 980 degrees, 980 newtons. That means that FGY equals 980 newtons times the cos of 20, which equals approximately 921 newtons. That's FGY. Now, if FGY is equal to 921 newtons, let's go back over here. That means that Fn is also equal to 921 newtons, just in the opposite direction of FGY. FGY is down into the ramp. Fn is straight out of the ramp. And so Fn, so let's give this direction, down and to the right, in the negative y prime direction. Fn equals 921 newtons in the positive y prime direction.